In this video, I introduce computer vision as one of the fast-growing disciplines in artificial intelligence. Computer vision is the eye of AI. The goal of computer vision is to develop machines that can see and interpret the visual data as we humans do effortlessly. After watching this video, you will be able to describe how a digital image is represented in a computer and explain how image processing is used to extract visual features from an image. Computer vision operates on visual data, where image is the most known type of visual data. Here we take a close look at what a digital image means for a computer. An image is stored in a computer as a matrix of numbers, commonly known as pixels. The simplest form of an image is a binary image, where black pixels are represented by 0 and white pixels by 1. A binary image is a black and white image as there is no color information encoded in the array. Here you see the black and white 35 by 35 pixel image of Flix the cat on the left, and the corresponding binary array representing on the right. You could clearly see the shape of the cat even in the array representation. Another colorless image is a grayscale image, where instead of binary values of zeros and ones, the image information is encoded in 8 bits. In other words, the pixel can take values between 0 to 255. This is a sample of MNIST dataset, a very well-known machine learning dataset of handwritten digits. A grayscale image, as you can see, shows a shade of gray because of the wider range of numeric representations. Now we look at the digital representation of a color image. A color image requires more numbers to encode color information compared to the grayscale image. Commonly, there are color channels used to store a color image in a computer, RGB, which stands for red, green, and blue channels. Let's take this example of colorful vegetables to visualize 3 arrays of channels of RGB. Zooming in a small area. This is a rectangular window on a red paprika. Let's look at the array representing the red channel here. One expects that the values in the red channel to be high since the zoomed area contains a red object. The green channel appears to be quite sparse, meaning that there are not high-value green pixels in this region, and indeed there are many zero in the G channel. And the B channel, that represents the blue pixel values, contains rather small values. Note that all colors are represented as a combination of these 3 channels. For example, white color is represented with 255 in all 3 channels, and black as 0 in all 3 RGB channels. Beyond the digital representation of an image in terms of numbers and arrays, there is another space within which an image exists. I would like to call it the semantic space of an image, which contains the meaning of an image. For example, in terms of the objects that are represented in the image. We as humans commonly describe an image with a natural language that is abstracting the objects and concepts that are represented in the image with words. In the example of vegetable image, the semantics are, for example, the foreground and the background in the image. There are more granular semantics in the image. For example, the objects in there including garlic, paprika, pepper, and tomato. Depending on the image, various information may be extracted. The goal of computer vision in image analysis is to extract semantic information from images, that is going from representation space to the semantic space. This information is referred to as a computer vision task. To perform a computer vision task, we need to extract the visual features that are associated with the semantic information to be deducted from the image. Let's take a look at one of the most celebrated computer vision tasks of all time, image classification. And of course, the task of cat and dog recognition. In our example, we would like the computer to assign one of the two labels, cat or dog, to each image. This is called binary image classification because there are only two classes of objects that may appear in the image. As human, we develop the skill to see and categorize things very easily without explicit reasoning, including recognizing the cats from the dogs. We might be able to explain the visual features that we use in our head to do this classification task. Among them, the shape of the animal object. In the early computer vision area, image processing is used to extract visual features from an image. Image processing uses spatial filters to extract visual features from an image. An example of a spatial filter is the edge detection filter. By applying an edge detection filter, one can extract the shape or the boundary of the objects in the image that can be further used for classification of an image. Let's apply an edge detection filter to these images. These kind of filters are used also in software packages like Photoshop. In the left, our edge detection filter can pick up edges that are determinant for the shape of the cat. The same goes for the dog. You see that simple filtering operation can extract the visual features that are essential and even sufficient for classification of objects in an image. We looked at one visual feature, the edges, in this example. However, more visual features can be used for the classification. For example, texture and colors. But what is this filtering operation that we talked about? Spatial filters are 2D arrays of numbers. They are also called kernels. Here we have a 3x3 filter that is an approximation of the scaled version of a Gaussian kernel that is used for blurring the images. Let's assume that we have a 4x6 image. We want to apply the left kernel to the right image. In mathematical terms, we convolve these two-dimensional signals. The operation is called convolution. Convolution is performed by sliding the filter over the image, where you multiply the corresponding array elements and then summing over them to generate a single value. That single value is a feature. In this slide, you see that our 3x3 Gaussian filter is overlaid with the top left corner of our image. The red values correspond to the filter values that are multiplied with the pixel values. The feature is generated by summing up the 9 values in the red window that are adding up to 13 here. Therefore, the first value in our feature map, that is the 2x4 array, is 13. By repeating this operation, we can fill up other feature values in our feature map as follows. This red feature map is the cropped, blurred image. Note that to have a correct scale for our feature map, we need to normalize it to the sum of the values in the kernel, that is 16 in our Gaussian example. The convolution operation is one of the essential building blocks for a modern computer vision that is evolved from image processing to data-driven machine learning paradigm. You need to understand the convolution to be able to understand the concept of convolutional neural network, or in brief, CNN, which is at the core of computer vision these days.